we have a plane wave at a frequency of 171 hertz. Okay, in plane wave that's propagating 175 hertz. It has a sound pressure level of 40 decibels. 20 micropascal reference. This is something that is supposed to teach you. So, first question is, what is the pressure? What is intensity? What's particle velocity? Okay. What do you know and what do you not know here? You can't just write, you have to think. What do you know and what do you not know? Plane wave. Freely propagating plane wave. So space doesn't matter. If it's not reflecting in front of something, then it would matter. But this is just an open field plane wave that's propagating. So because it's a constant phase, it doesn't diminish as it moves along, same amplitude everywhere. Don't go back, think, respond to me. What do you not know here? So you know everything.
We don't know theta.
You don't, theta, what's theta?
Direction of the plane.
Why do you need it?
If it is normal to the wall.
Well, the question is, a plane wave that's propagating, it has a particular frequency and particular amplitude, defined as 40 decibels. It's asking you what the pressure is. It says nothing about reflection. It doesn't say anything about a wall.
You know everything.
You know everything. Okay, what's the pressure? How would you calculate it? Okay. You don't know everything. What is this? We can write it. Let's say this is air, 343 meters per second. B is intensity and C is the particle velocity. This is the simplest possible problem. Can't be simpler than this. Just to set the reference frame. There's something here that you haven't seen, at least in this class. I'm trying to understand whether you know that you haven't seen it or not. Maybe you have seen it elsewhere. What does this mean? See, we never talked about this. What does it mean? Do you know? Amplitude may be, okay. What kind of amplitude? Yes?
It might be effective pressure.
No. You know it. You have seen this. Okay, now, like in earthquakes, Richter scale, okay, because the range is so large that we use logarithmic scale to compress it, okay? So each time you go up on a Richter scale, it isn't just 1 point, but it is quite a bit of energy, 10 times, I think, okay? So the definition of sound pressure level is in decibel scale. Decibel. This actually is after Alexander Graham Bell, and this is, as you know, decimal, 10 base. And the definition here is LP, normal definition, log 10 base, pressure over pressure reference square. Now, when you use the decibel scales in these, we always have energy-like or power-like quantity, the ratio of the power-like quantities. Okay? And this P0 is the reference pressure, and that's 2 times 10 to the minus 5. Is it? Yes, minus 5 pascals. And of course, Pascal is 1 Newton per meter square. And this value corresponds approximately to the lowest level of sound a human being can hear. Okay? So if sound pressure is equal to P0, if sound pressure is equal to reference pressure, what would be the sound pressure level? Think quickly. If P is equal to P0, what would be the sound pressure level? Say again? 0, exactly. 0 dB is the reference where we can barely hear sound. That's why we pick it. Okay, so going back here, of course, commonly we write it as log P over P0. And you can also write it in a number of different ways. And so on. This is a constant. But regardless, that's the one. Now, similarly, you can write intensity level. In this case, intensity itself is a energy-like or power-like quantity, so we do not oh yes, I did give you in the homework problem some definitions. We do not take a square, and I0 is 1 times 10 to the minus 12 watt per meter square. I think that's what it is. Yes. Okay. So the question here is, if you have LP equals 40 dB, what will be the sound pressure level? Sound pressure itself. What is P? Well, very simply, 40 is equal to 20 log P over P0. And from here you have 2 log so sound pressure would be 2 10 to the minus 5 10 2, so that would be Pascal. Okay. How would you find the particle velocity or intensity? You cannot? Okay, why not? Okay. Well, what intensity is... I see what you're getting at. That's from the derivation. But what intensity is, where shall I do this? Intensity definition, it's a vector quantity, number one. and it's defined as, oops, particle velocity. Okay, so its amplitude is the multiplication of the RMS values so you have Pu over 2. Now, in a plane wave, we do know the relationship between particle velocity and pressure in a plane wave in a normal incidence. And what is that? Does anybody remember? Remember, it comes from and that gives us, it's through the impedance, okay? P is on a simple, normal, plane wave, particle velocity and pressure are related through the impedance, okay? So if you substitute that, then you have, okay? Does it make sense? Yeah. And that, of course, for air, we can say, let's see, 2, 10 to the minus 3 squared. And you can calculate what the intensity is in watt per meter square. I think I did that. Okay, once you write it in, let's just review what we just did, because you're learning a couple of new concepts through the example. Okay. By the way, please be careful when you write dB. This is also dB. It's lowercase and capital B. Lowercase d, capital B. Okay? That's the correct way of writing it down. Okay. Now, we said very simply, see, we never use the frequency, not on this part anyway. And we said if you have a plane wave, 40 dB, what would be the pressure, intensity, and so on. So the first thing you learned was definition of levels, okay, sound pressure level, intensity level. You can write the same thing about power level. There's a reference for it, which is the same number, actually, because it's just intensity times area. And you learned that. And the second thing you remembered is the relationship for a plane wave between pressure and particle velocity through impedance of the fluid medium. If it's water, this is a different number. If it is air, this is 416, 417, density times the speed of sound. Any questions on this example? You were confused looking for an angle. There's no angle on this one, but there will be in the future problems, okay? Just a straightforward example. All right. Let's now look at sound penetration into from one fluid into another fluid, okay? And then that will give us what you know as the Snell's law, refraction angles. Let's see. Okay, once again, we have an incident angle. Let's see, this is medium 1 and medium 2. The first medium is characterized by density and speed of sound of that medium, and the second one is characterized, again, with the respective values. And so sound pressure, as you know, these are plane waves that are coming onto the second fluid and reflecting. But not only does it get reflected, but some of it is transmitted. Now we have a different phenomenon. Okay, some of the energy can go into the other fluid. And once again, let's define the angles that the directions make with the z-axis, and see if we can write the pressure field on both sides. Okay, in the upper part we have a pressure field that's some of these. See if you're able to write that. Yeah, see if you can quickly write it down. Let's see what you have done. Okay, we'll write the incident plus reflected, and we'll use, once again, the reflection coefficient for the reflected one. Let's see, we have okay. Something wrong? You have a question?
Yes, the place of theta I is different than what the first one.
The place
Or
of...
we will change cosine to sine, sine to cosine.
No? Are they? Let me see now. Yes, x and z. Okay, you're right. Yes, let me just see for a second here. So this is z, cosine should be on the z side. Okay. Let's see now. Let me make sure I'm doing this. Okay. X is no. X is sine theta I. Yes, it's always positive. Let me do this. Let me scratch it and do it right. Okay. Give more space. Okay. So it's Zx theta. Okay. Let's do it. Sine theta I. Okay. Okay, okay, this is the mistake. Yes, okay, good. Yeah. I is coming down as cosine z, kx, sine theta. Okay, right. Okay. Should be okay now. Okay. Okay. In the reflected side, once again, we have a harmonic, but this time we have e to the one other thing. Okay, in this equation, all the k's are k1. Why is that? Exactly, because k is equal to omega over c. Omega is, of course, the same. Frequency doesn't change, but speed of sound will change it. Okay, so these are all K1. IK2 Z cosine theta T plus IK2X sine theta T. More questions? Yes, go ahead.
The first equation, I think the sign of the power term should change.
Which term?
The sign of the power term, e power,
Here?
the first term should be plus, the second term.
You mean this should be plus?
And this
Okay, let's see. No, Z is going down in the opposite direction.
but there's a minus.
But it's not multiplying that. That's why I separated it, just to make sure. You mean this minus? Yeah, if, if it were like this, yes, but they're separate. I separated it just to make sure. Now, okay, to make it easier. Okay? You sure? You follow? Okay, yeah. Now, what we have here that we need to remember is continuity at z equals 0. Suggests that pressure must be the same on either side, okay, adjacent. Otherwise, then you have a pressure discontinuity, and that's not physically possible in these linear cases. So what does that mean? Let's apply pi. We said z0, so the I k1 x1 sine theta I. And z equals 0. Okay, what does it tell us? For this equality to hold, once again, the exponents must all be the same. Okay? So for continuity to hold, exponents must be the same, and that means k1 sine theta I must be equal to k1 sine theta r, and that must be equal to k2 sine theta t. From the first two, we can already figure out what we have before. incident and reflected waves must be the same. Okay? But this is the other two. We have to take into consideration the differences in the wave number. So that gives us what's commonly known as the Snell's law. That is ratio of the sine of the angle to the speed of sound in one medium is equal to the same ratio in the other medium. That's all it says. Let's continue with this now and talk about the reflection and transmission coefficients. But we'll just cover pressure at this point. Yes, you have another question? You sure? Okay. All right. Reflection and transmission coefficients. To do that, we use two boundary conditions. And one of them is that pressure must be continuous at the boundary, and second one is particle velocity must be continuous at the boundary also. Okay? And the first one tells us okay, we can write this in terms of 1 plus R okay. R is the amplitudes of reflected to incident, and T is the ratio of the transmitted pressure amplitude to incident pressure amplitude. Let's now look at the particle velocity continuity. The particle velocity is obtained once again by taking the derivative in the z direction, and that we can express as, let me see, minus yes. Okay. So we have two relationships. That we can use to determine these values. Okay, let's continue on this side while you're able to see that. Okay, what did we do? We express the incident plane wave, reflected plane wave, and transmitted plane wave in general terms. Okay, and then we applied the boundary conditions at the interface, suggesting that pressure and particle velocity must be continuous. And using those boundary conditions, we end up with two relationships. You have a question, Said? Go ahead.
I couldn't figure out PI's one of, yes.
This? Oh, what we do here is if you divide the whole thing by pi, this would be 1, this would be r, and this would be t. So I pulled it out here. Okay? Yeah. All right, so we have relationship 1, and then we have a relationship this one we'll call zeta. It's again a ratio of the impedances between the two. Then let's see quickly, 1 minus r. Actually, before I do that, this is fine, but what I want to do is just divide these, okay? Yeah, so that we can get rid of the t expression here. So if we divide them, it's a lot easier. 1 minus r. Then we have 1 over zeta cosine theta t cosine theta I. Okay. Now we can simplify this. Okay, from here, change the signs here. Something's not right. These should be upside down. Sorry. It's embarrassing terribly. Let's see now. Let me rewrite this quickly. Let me just rewrite that. Particle velocity. Of course, it's particle velocity, yes. Particle velocity should be minus cosine theta I rho 1 C1. This is the velocity. Theta cosine. Okay. I take pi here and cosine theta I over rho 1 C1. This will be 1 minus r. And this will be, if I do the same, cosine theta t rho 2 C2 bt. Divide both sides by pi. That would give me, oh, this should be negative. Okay. Opposite direction, so this will give me 1 minus r. I knew something was not right. Okay. Flipped. Let me make sure that that's correct. Yep. Okay, so okay. Now let's try to divide it again. Okay. All right. The same problem here. Okay. This whole thing is that I'm making a mistake by taking it as a fraction. Guys, I owe you one. Okay, sorry. This zeta is part of this. It's this guy. Okay. So, okay, now this is correct. Something wasn't coming out right, but okay. There we go. Whew. Finally. Okay, now that's the reflection coefficient in terms of impedance and the angle. But there's some issues here that we need to be careful about. Okay. Right, cosine theta t. Yes. Okay, can I have your attention just for a second? This transmitted wave, okay, it has a x component and also a z component that goes in the other direction. Now, what we are, if you remember what we have done before, what we're saying is when the wave comes in, incident wave, it does have a pressure distribution here, particular wavelength, etc. That is definite, and it is there, and it is real, because a forcing function, if you think about the sound pressure wave as a forcing function, this component has to exist and be real. And that component corresponds to which part? Sine theta t part, okay, the x part. So what we have here is a cosine term, okay. So let me make sure that we understand this, because this really is a critical part of sound transmission from one medium to the next. Okay, so transmitted pressure wave component in x direction must be real. And what that means is K2 sine theta t must be real. And from here we say sine theta t must be real. Okay, if that's the case, okay, what we need to do is write cosine theta t in terms of sine. In fact, what I want to just demonstrate once again is okay, so waves are coming. Really, the strictly correct way to say this is it's the incident wave. Okay, the incident wave has a component in the extraction that must be real because it's physically that's what we're doing. Okay, I would say instead of this even, okay, incident wave, and that will also make the transmitted wave. Incident wave must have and does have a real pressure. Okay, that's the existing, that's the forcing function that we're providing. So what we want to do then is express cosine theta in terms of theta incident. And how can we do that? We have a relationship through the Snell's law. So first of all, cosine theta t we can write as 1 minus sine square theta t. And sine theta t, we already have the expression for. Okay. I want to draw your attention just for 1 second. You understand these, but I want to get something written here, just rewrite it a little bit differently. Okay? You remember what this is? Earlier we talked about the speed that's along the surface. If this was C1, okay, this being the angle, or this being the angle, this is C1 over sine theta I. Okay, so we're looking at the speed difference, speed on this medium, and speed with which the phase speed the surface experiences. That's the ratio. Okay, if one is, you can see here now, if the, let me just rewrite it one more time, C2 divided by C1 sine theta I. Sine theta. You can see here, if this is larger than this is going to become an imaginary number. And we'll see what that means when it becomes imaginary. Okay, when the speed of sound becomes imaginary, then it's not going anywhere. Let me leave this. What we want to do is take that value and substitute it into the reflection equation. Now we have coefficient of reflection This is now the actual coefficient of reflection equation. Now, what happens if C2 over larger than 1, then we have an imaginary component. Okay? And the new value would be somewhat different. Take a look at this and see what happens when theta I is equal to pi over 2. What happens to it? And what does it mean? Don't write, just think about it for a second. If the incident angle is pi over 2, what does it mean, and what happens to the reflection coefficient? Oh, this is the, sorry? Okay, yes. What does that mean? Resilient surface characteristic. But physically, what is going on? What does pi over 2 mean? What is the direction of the plane wave? Parallel, not perpendicular. Okay, see, right, this is the angle, so it is going this way, and these are the waves that go. But physically, this is not realistic. Why is it not realistic? Because plane wave means it's same phase everywhere. But here, it has to change. It's interacting with the surface. So you don't really have plane wave here, one. Secondly, by and large, there's a lot to be said about it in physical systems, plates and such. This also has a very interesting and physically, acoustically, very important characteristic that we'll get to later on. So that's the effect of Snell's law and reflection from another medium. In a few minutes, in the next unit, we'll look at, this is a pressure reflection coefficient, we'll look at transmission as well as the power and intensity reflection coefficients. Okay.